G'day everyone, wherever you are in the world, and welcome to this presentation on developing site-specific odour industry receptor separation distances. I'm Andrew Balch from Air Environment in Australia, and my collaborator on this project was Prasha Xylem from Taswater in Tasmania, Australia. I'll be sharing our collaborative work on developing and validating a scientifically rigorous method for determining evidence-based buffer distances using one of Taswater's wastewater treatment plants, our case study site. Our case study site was an urban wastewater treatment facility situated next to an estuary. The facility operates a secondary activated sludge treatment system with chlorine disinfection and comprehensive odour control measures. The plant services approximately 22,000 EP with a current average daily inflow of 4,470 kilolitres per day, which is well within its licensed capacity. The treatment process encompasses primary and secondary treatment, anaerobic sludge digestion and biosolids dewatering and storage facilities. The facility's urban and estuarine location presented typical challenges for field odour assessment and management with sensitive residential receptors in close proximity, inaccessible private property and water limiting survey locations, and complex meteorological conditions influenced by both terrestrial and marine atmospheric boundary layer processes. The plant has a mixed odour control approach that's typical of Australian wastewater treatment plants. What makes this particularly interesting for our method development is the contrast between, is there a problem with the YouTube? Is there a problem with the feed, is there? Someone's asking a question, I think.
No, we can hear you loud and clear. You can continue.
Oh, okay, fantastic. Right. The plant has a mixed odour control approach that's typical of Australian wastewater treatment plants. What makes this particularly interesting for our method development is the contrast between controlled and uncontrolled emission sources within the same facility. The primary treatment area, including the inlet channel and 3 sedimentation clarifiers, is fully covered with air extraction for odour treatment in 3 biofilters. However, during the emissions audit, these biofilters were determined to be significantly underperforming and responsible for 97.8% of total plant odour emissions. This constitutes a non-routine emission source, which actually helps to assess odour buffers, which are typically required for the mitigation of impacts associated with non-routine residual emissions rather than normal emissions. In contrast, the secondary treatment area tanks, the selectors, anaerobic and aerobic zones and clarification are open to atmosphere, creating odour sources. The anaerobic digester air gases are flared for both safety and odour management, while the sludge dewatering building is ventilated to biofilter treatment, and the sludge storage bin is covered and ventilated to an activated carbon filtration system. Importantly for our research, this situation created ideal conditions for methodology validation because we're able to test our approach against both controlled and uncontrolled emission scenarios within a single facility. We collected 66 odour samples with minimum triplicate sampling across all treatment areas. Biofilter surfaces were sampled over 4 zones, inlet channels at a time series during peak flows, and secondary treatment tanks repeated over 2 days. All samples underwent odour concentration analysis by dynamic olfactometry and qualitative characterisation. Our dispersion modelling employed Tapham Calmette-Cowpuff suite with a representative meteorological year. We statistically validated meteorological model performance and developed comprehensive emissions inventories comparing multiple previous audits. Multiple scenarios assessed entire facility and individual odour source groups with sensitivity analysis revealing suboptimal biofilter performance. This slide shows the predicted ground level odour concentrations for 2 key odour sources, source groups. That is the sources which have similar odour characters when observed downwind. That is similar within each source group. Each source group is obviously different, the primary and secondary treatment areas. We then conducted 15 2-hour ambient odour surveys over 5 consecutive days with coverage between 6 AM and 9 PM. Each survey lasted over 2 hours using 5-minute measurements at 10-second intervals. We recorded odour intensity, hedonic tone, meteorological conditions and odour character, and identified source information. This slide, exported directly from our Plume Mapper software, illustrates all of the 156 measurement points collected over 15 surveys. The colour coding relates to the observed odour intensity. The site boundary and odour sources are all shown on the map. You can see in the map that white dots represent no odour was detected, yellow is very weak, green is weak, and blue dots are moderate or obvious odour. Using Plume Mapper, we can easily filter the observed odour data by source or any other combination of measured parameters and calculate the maximum odour footprint. Plume Mapper also presents data graphics like this box and whisker plot, which shows the distribution of downwind distances in which odours were observed at different intensities. The slide shows the spread of odour observations and the odour footprint, that's the contours, of the primary treatment area odour sources. Here you can see the spread and odour footprint of the secondary treatment sources. Well, this slide shows the spread and odour footprint of all plant sources combined. The field odour surveillance data suggests that the odour modelling may overestimate the plant's odour footprint. So we can ask ourselves some questions. How does this odour footprint compare to the odour model predictions? Are the field observations representative of the highest impacts modelled for the 99.5th percentile? That's according to the local regulatory odour criteria. Are the field observations conducted the worst case time of the day or the year? And do they capture the impacts under worst case emissions and or meteorological scenarios? So we move on to a model validation. This is our next critical step. To ground truth the dispersion model using our field odour surveillance data. We modelled meteorology for the survey period, assimilating survey observations at sub-hourly time steps to capture local atmospheric conditions. We then modelled our odour emissions inventory from the survey for each 2-hour survey period and systematically compared model predictions to field surveillance observations. This comprehensive validation approach allowed us to identify discrepancies between laboratory-derived emission rates and actual field conditions, providing the foundation for model calibration and scaling factor determination that would enhance prediction accuracy. Our model evaluation revealed systematic discrepancies between predicted and observed odour impacts. The dispersion model over-predicted the impact of primary treatment area odour source emissions while under-predicting secondary treatment area emissions. This raised critical questions. How significant were these discrepancies? Could we correct them systematically? And crucially, were our field observations representative of peak impacts or at least the percentile values that align with regulatory assessment criteria? For example, in this case, the 99.5th percentile. These findings highlighted the importance of field validation in odour assessment methodology. To address these discrepancies, we applied the European Field Ambient Odour Plume Measurement method for our observed odour footprints. We defined one sniffing unit odour isoplex representing the detectable versus non-detectable boundary for each odour source group by character. We then compared observed one sniffing unit isoplex with model concentration isoplex, establishing that one sniffing unit equals one odour unit for calibration purposes. The contour on each of these plots represents the closest model contour to the one sniffing unit line determined from the field observations. We calculated source-specific scaling factors through systematic comparison of observed and modelled plume boundaries. We determined mean scaling factors for each source type. The average emission rate scaling factors revealed significant discrepancies. For instance, the primary treatment area odours were overestimated by approximately a factor of 4. Secondary treatment area odours were underestimated approximately by a factor of 7. We developed a full-year model using our validated TAPM CalMet cowpup configuration and applied the ground truth emission rates incorporating our scaling factors. We identified the furthest field measurement locations where detectable odour was observed during our field surveys and extracted annual concentration time series at these critical receptor locations. This approach enabled us to determine the percentiles where concentrations exceeded our assessment criteria, forming the basis for evidence-based buffer distance determination. Here you can see the difference between the original model to Odour Unit for the whole plant and the now calibrated or modified model. We generated concentration isoplex for various percentiles using either 2 Odour Unit concentration criterion or equivalent to moderate or obvious odour intensity as options. We then calculated statistical distributions of source to buffer distances. This analysis showed a primary treatment maximum distance of 557 metres versus a secondary treatment maximum of 457 metres, with area equivalent radial buffers of 274 and 226 metres respectively. These figures illustrate the evaluation of alternative buffer approaches such as conservative concentration-based percentiles, area equivalent radial buffers, and actual meteorologically adjusted buffers. We selected the most appropriate approach considering sensitive receptor distribution and regulatory requirements while keeping in mind the uncertainties in the measurements and consequent scaling factors. You see on the left, the image on the left shows the primary and secondary treatment plants. That's based on the model of the distribution of winds. And then if you take those areas and make it area equivalent, but make it a radial buffer, you get the buffer on the right, which is a more typical static buffer a distance for a treatment plant. But it obviously ignores the prevailing wind directions. We then compared the calculated site-specific buffer to the actual state's existing regulatory buffer. The regulatory buffer is a static 400 metre radial buffer from the site boundary. In this image, we have meteorologically adjusted all the buffers for comparison. This retains the buffer area while skewing its shape to account for meteorological biases. In this case, the regulatory buffer is more conservative in all directions except for the direction of the prevailing wind to the southeast of the plant. We've acknowledged several limitations requiring enhancement for broader method application. We identified the need for expanded temporal coverage across multiple seasons, increased survey frequency, and laboratory-based odour concentration intensity relationship characterisation using the VDI 3882.1 protocols. Enhanced spatial coverage requires multiple assessment teams and better land access to survey locations. For transferability in the wastewater sector, we must develop wastewater treatment specific calibration protocols and scaling factor databases across facility types. This methodology just demonstrates significant scientific rigor through ground truth validation, combining laboratory emission testing with field observations. Our advanced cowpup modelling integration using 10-minute time steps and European ambient odour survey method, plume surveillance methods, provides systematic model calibration, achieving reasonable regulatory alignment, deriving 274 metre versus 400 metre planning scheme standards, while providing site-specific refinement based on actual emission characteristics. This standardised transferable framework bridges the gap between generic regulatory buffers and facility-specific separation distances, enabling cost-effective risk management that prevents over-conservative restrictions while providing defensible compliance distances with comprehensive quality assurance protocols, ensuring reproducible results across industries. Thank you. Thanks for listening.